Hello everyone, welcome to Bilecik Algebra and Number Theory seminar. Uh, Today's speaker is Professor Masanobu Kaneko from Kyushu University, and he will speak about an introduction to finite multiple zeta values. Thank you.
Thank you for the introduction. So thank you, Ilka, for your kind invitation to this seminar. It's my great pleasure to present you an introduction to finite multiple zeta values. So this is oh, just a moment, how to, ah, joint work with Don Zagier. So we finally finished writing up our joint paper. It's a long-term project started more than a decade ago. But anyway, we finished just one paper. But before talking about the finite multiple zeta values, I want to give a brief introduction to the classical, so real multiple zeta values. So sometimes MZV for short. So this is a real number defined by this nested infinite series. So K1 up to Kr is a given positive integers. And this zeta of K1 up to Kr is defined as this sum 1 over M1 to the K1 up to Mr to the Kr. And M1 is less than M2, less than Mr. So this number R is sometimes called depth of this multiple zeta values. And the outermost exponent, Kr, should be bigger than 1 for convergence. So we assume that. So this or these are just simple real numbers. But, so amazingly enough, so there are lots of nice structures behind them and connects to various fields of mathematics, such as this I listed here, some topics, knot invariance, quantum groups, mixed state motif, etc. And even in physics, so this Feynman amplitude is a real number associated to the so-called Feynman diagram, which describe the interaction of elementary particles. So this Feynman amplitude has really real connection to the real world, so mystery of universe. So MZV is, excuse me?
No, I think
So,
all is fine.
okay, so but it was Euler who studied this MZV. In the case of R equals 2, so that's almost 300 years ago. But the case of R equals 1, this R is a number of indices, K1 up to Kr. So R equals 1 case is, as I think all you know, this is so-called Riemann zeta values, but it was actually Euler who evaluated the values of Riemann zeta function at positive even integers as a rational multiple of power of pi. And this is the exact formula where B2n is Bernoulli numbers. And he also evaluated negative values. This is a divergent case. But anyway, this will be, we will use this in the finite MZV story. Okay, these are, I think, famous formulas. Bn is Bernoulli number. Okay, so R equals 2 case, sometimes called double zeta values, is So it seems it was Goldbach who started looking at this double zeta values. So this is a letter, first letter to Euler from Goldbach. The original was German, but this is an English translation. And he mentioned, yeah, on that occasion, I came upon the summation of some other series, which, etc. So this is double zeta values, except that this allows the equality sign in the definition. So, but essentially, this is double zeta values. And this is Euler's first response. A month later, and he was so excited, and he thought these objects very beautiful, and he discovered some formulas describing this alpha, beta, gamma are, I think, the double zeta values, and the capital A, B, C are Riemann zeta values. So he wrote these double zeta values in terms of Riemann zeta values. And much later, Euler wrote a paper on this double zeta values. This is in Latin, meditationes circa singulare serierum genus is the title. Yeah, so he mentioned the Goldbach at the beginning. All right, this is just history, but modern research so explored in around 1990s, and a great source of inspiration was Don Zagier's conjecture made in 1994. So he considered the space, Q vector space, spanned by this multiple zeta values of fixed weight k. Weight is the sum of the indices. So this R also varies. So he considered the Q vector space finite dimensional, because for a given k, there are only finitely many k1 up to kr indices of weight k. Okay, and he did lots of numerical computations using Paris GP, and he conjectured that the dimension of weight k space zk, this calligraphic z sub k, is the space spanned by mzv of weight k, is given by a Fibonacci-like sequence. Actually, this is called the Padovan sequence. So this recurrence relation is a three-term recurrence, but the dk is equals to the sum of 2 before and 3 before, d sub k minus 2 plus d sub k minus 3. So I give you the table. So for weight 0, we so empty index is, we regard the empty index as a weight 0. So this is simple, and zeta of empty index is we put that is 1. So this is just rational numbers, and there's no weight 1 MZV because of this convergence condition. So this KR should be bigger than 1. So this zeta, there's only one weight 2 MZV, which is zeta 2. And there are two MZVs of weight 3, zeta 3 and zeta 1, 2. So zeta 2, 1 is divergent. Also, zeta 1, 1, 1 is also divergent. It's not allowed. But so this last column, 1, 2, 4, 8, 16, 32, is the power of 2, is the number of indices of given weight. So weight, for example, at weight 4, there are 4 weight 4 indices, 4, 1, 3, 2, 2, 1, 1, 2. But the actual dimension is just 1. So these are the conjecture sequence of dimensions. And the actual number, so for example, at weight 15, there are more than 8,000 MZVs of weight 15, but conjecture dimension is far smaller, 28. So this is the Zagier's conjecture. And he, in his paper in 1994, he mentioned the deep theory like mixed state motif or quantum groups, etc., are behind this sequence or this space. So that ignited the interest of many people, and lots of works started to coming out. Yeah, and maybe less than 10 years later, Goncharov and Terasoma proved that this dimension of zk is actually bounded from above by this sequence dk. Goncharov's paper never published, and later he and Deline wrote a joint paper describing his proof. Okay. But this is the upper bound, but the lower bound is it is believed that is out of reach at the current status of knowledge. So we do not know any single k bigger than 4. So so up to 4. This is the dimension is 1. That is okay, but there's no known k bigger than 4 such that the dimension is actually proved to be bigger than 1. So we do not know any independence result. For instance, we do not know zeta 5 and zeta 2, 3 are linearly independent over Q. Yeah, such kind of irrationality or independence result is very difficult to prove. Okay. So this suggests that there should exist many relations linear relations among MCVs. So for later purpose, I describe one example of relations called double shuffle relations. So for example, let's look at the product of zeta 2 times zeta 3. This is by using the defining series. Then this is just this two-dimensional sum. M and n are positive integers, and the 1 over m squared and n cubed. So we divide this two-dimensional lattice points m and n by this is the above diagonal, this is below diagonal, and this is on the diagonal. Then each sum gives you MZV. So this order is important. So this first one is zeta 2, 3. And the second one is n is less than m. So n comes first. So 3 comes first and then comes 2. So zeta 2, 3 and 3, 2 are different. And the final one, m equals n, so just m to the fifth. So this is zeta 5. Okay? And the general multiplication of two MZVs are computed in a similar manner as a sum of MZVs. So this is sometimes called Staffel product or harmonic product. And we write symbolically, this the right-hand side is 2 star 3. So this is a product on the space of formal sum of indices. So 2 times star 3 is 2, 3, and 3, 2, and 5. And we extend this symbol zeta linearly to this formal linear combination. So this zeta 2 times zeta 3 is zeta of 2 star 3 is our notation to describe this relation, product relation. And there's another way by using integral expression of MCV. There is an integral, the so-called iterated integral expression of MZV. The first example, zeta 2, is this two-dimensional integral, dt1 over 1 minus t1, dt2 over t2, over this cone. So, and zeta 3 is a three-dimensional integral of this form. So this differential form is either dt over 1 minus t or dt over t. And zeta 2, 3 is like this. I don't explain in detail the rule, but the dimension of the integral is the weight. So 2, 3 is weight 5. This is 5-dimensional. This part, first two part corresponds to 2. And this next three part is corresponds to 3. So like this. Yeah. So then let's compute again the no, not again, but compute the zeta 2 squared. Then this by using this integral expression, then the product is just a Cartesian product of these. So this four-dimensional integral, and we can divide this domain into the 6 pieces. We can ignore the lower dimensional piece, like T1 may be equal to S1, but that is measure 0. So we only look at these 6 subdomains, and T1 is should be always less than T2, and S1 should always be less than S2. Those are the conditions, and there are 6 ways of ordering T1 up to S2. And then, excuse me. So each integral is again MZV. And in this case, each is either zeta 2, 2, like this, or zeta 1, 3, like this. So this product using integral is equals to 2 times twice of zeta 2, 2 plus 4 times zeta 1, 3. This rule is called shuffle product, like a shuffle of cards. So in this case, zeta 2 square is zeta of 2 shuffle 2. This is again the formal multiplication of formal space of indices. Okay. So we have 2 ways of expressing the product as a sum of MZVs. So then we can equate these two to obtain one linear relations. And in this case, zeta 4 equals 4 times zeta 1, 3. This is an example of double shuffle relations. But so maybe you notice this product respects weight. So zeta 2 times zeta 2 have weight 4. So the relation obtained in this way, the least weight is 4. We cannot obtain the weight 3 relations in this way, but there is relations due to Euler, the famous one. So there are two MZVs of weight 3, zeta 3 and zeta 1, 2, but actually they are equal. This is due to Euler. So how to deduce this? And we can have one way to deduce this, like in the same way as before. That is regularized double shuffle relations. So let's pretend zeta 1 is convergent. Yeah, this is a divergent one, but formally we play the same game. So this shuffle, the series product, zeta 1 times zeta 2 is 1, 2 plus 2, 1 plus zeta 3. But this zeta 2, 1 is divergent. So this is, in a sense, this is not the actual identity. But let's proceed. So this is an integral. So integral correspond to zeta 1 is from 0 to 1 of dt over 1 minus t. This is a divergent integral. But let's apply the same shuffle rule. Then this is equal to twice of zeta 1, 2 plus zeta 2, 1. This term is divergent. But if we equate these, then the divergent term cancels, and we obtain this Euler's zeta 3 equals zeta 1, 2. So in the general case, it's not that simple, but there's a way to extract by using either series or integral the convergent finite values from the divergent indices. This process of regularization and this zeta star and zeta sha of k1 up to kr, in this case kr can be 1, is are called regularized multiple zeta values. There is a certain process to extract these finite values from the divergent indices. Then it's a folklore conjecture that this regularized double shuffle relations, which I didn't explain in detail, but those are enough to describe all linear relations among MCVs. And nowadays, various other relations are known, which are conjectured to give all relations of multiple zeta values, such as associator relations, Kawashima relations, confluence relations, integral series relations, etc., etc. But it's not yet fully understood that any one of these are really enough to describe all linear relations among MZVs. It's still, I think, open. There's another interesting conjecture given in the 1990s by Hoffman, who also started looking at the MZVs of general depth very early. So he conjectured that the space spanned by these MZVs over Q is generated by those with limited indices, either 2 or 3. And later Francis Brown proved this using the algebraic geometric machinery, so mixed state motif or motivic MCVs. And his work had a great impact and many important consequences, like the Deligne-Ihara conjecture, so-called, on the L-adic Galois representations. It was totally unexpected to have such a connection this simple MCV has. Okay, so these are the review of MCVs, classical. So let's move on to the finite MCVs. So this is a sort of naive thing. So for each prime p, let's look at the truncation of the original series at p. So before the denominator has p. So this is a finite sum, p integral. So we can reduce this modulo p to have an element in a prime field of elements, p elements. Okay. And it was Zagier who proposed to consider the collection of all these for all p, but not in a direct product, but instead the quotient of direct product of all p of z over pz divided by an ideal of the direct sum. So direct sum has all but finitely many components are 0. So from some point on, all 0, 0, 0. So what this mean is, so we identify two elements in the direct product if and only if they differ only at finitely many primes. So from some point on, they all coincide, then we identified and we consider this equivalence class represented by that element in direct product. So what is nice here is this is a ring with component-wise addition and multiplication, but not only a ring, but this is a Q algebra. So rational numbers can be embedded diagonally into this ring A. So this is a characteristic 0 or Q algebra, Q vector space. So we define a finite MCVs. So let's assume all Ki are positive integers, allowing Kr can be 1. So zeta sub A of K1 up to Kr is a collection of these finite truncation at each p, and consider this collection in the direct product and its equivalence class. We also denote by the equivalence class, also by this just a collection over p in a ring A. So this is a finite MCV. So we may consider similar problems as in the classical case, and it's rather surprisingly very similar looking relations hold in this new world of finite MCVs. So let's look at the example of low depth. So first, when the depth is 1, so the single index zeta a of k is 0, except when k, yeah, we only look at the positive integers, so it's always 0. But if we allow k to be negative, it's also 0, except when k is 0. This is simply because so each p component is this sum modulo p. But when the exponent k is not a multiple of p minus 1, then by elementary number theory, this is 0 modulo p. But k is given. So for given k, there are only finitely many p's such that p minus 1 divides k. But we can ignore those finitely many p's in this ring A. So from some point on, for given k, all this guy is 0 modulo p. So the representing element is 0. So zeta a of k is 0. And the next one, the depth 2 case, this is non-trivial, and the result is this binomial, this sign times the capital Z of k1 plus k2, where Z of k is represented by this Bernoulli number at p minus k. So for given k, p should be larger than k, but for big enough k, this p minus k is always positive, so we can ignore the finitely many small p's. So this is well defined, gives a well-defined element in A by Clausen-von Staudt theorem. This is P integral for big P, and k bigger than 1. So k is not 1. So I forgot to write that. But this k1 plus k2 is bigger than 1 when k are positive integers. And the proof is by using Secchi-Bernoulli's formula for sum of powers. So we want to compute this sum, finite sum, 0 less than m less than n less than p of 1 over m to the k1 times n to the k2. But because of the Fermat's little theorem, the exponent minus k1 can be shifted by a multiple of p minus 1. So this is congruent modulo p to m to the p minus 1 minus k1. And when p is big enough, this power is positive. And this m is from 1 to n minus 1. This so finite sum of positive powers of m. We have a formula due to Secchi and Bernoulli of this sum of powers. And then Bernoulli numbers appears. And after some computations, we end up with this formula. Okay, this formula will show up again later. There's also a dimension conjecture in the same game. So Q vector space. This is also due to Don Zagier. He conducted the numerical experiments. So let's again consider the Q vector space, this time in the ring A, Q algebra A, spanned by this finite MZVs of given weight. So K is fixed, R varies, Ki varies. And his conjecture is this is of dimension, again, this same sequence, Padovan sequence. But in this case, not d sub k, but the k minus 3, which is equals, by the recursion, is equal to the dk minus 2. And we later use this Z sub A, which is the sum of all ZK, ZAK. So the space of Q span of all MZVs, of all finite MZVs. Okay? When K equals 0, this is regarded as just a Q. So there are examples of relations. For instance, there is a famous formula called sum formula. It's a beautiful formula. The sum of, so this is a classical MCV. The sum of all MZVs of fixed weight and fixed depth. So this time R is also fixed. Then this is equals to zeta k. And as a finite MZV analog of this is due to Shingo Saito and Wakabayashi, is given again, consider the same sum with this condition may look strange because we have no convergent issue, but anyway, we put the condition this kr is bigger than 1 is equal to a simple multiple, in this case, not single something, but here comes this zk. Zk is this one, this Bernoulli Bp minus k over k modulo p. And this may suggest this Z, capital Z of k is an analog, in A analog of Riemann zeta k. Yeah. It's not only this formula, but there are many instances which suggest this Z of k is an A analog of Zk. And there's one nice heuristic explanation that is this. So this Fermat is Fermat's little theorem. Of course, this is nonsense. This zeta k, we shift the exponent by p minus 1. When p is large enough, this will be a negative integer. We have a formula of Euler. This is equal to this, as recalled in the first slide. This is Euler's formula, and this reduces modulo p to be p minus k over k. So when k is even, this capital Zk is 0 because Bernoulli number, odd index Bernoulli number is all 0 except b1. So when k is even, p minus k is odd for p bigger than 2. Yeah. But it's still unknown that Zk is non-zero or not when k is an odd integer bigger than 1. And this is implied by an infinitude of regular primes. But we do not know yet if the regular primes, there are infinitely many regular primes or not. It's conjecture to be so, but it's not yet proved. Anyway, we also come to this question later. So analog of double shuffle relations, we have a theorem. So for any index sets, K and L, this first relation is an analog of the Staffel, the star product, a version of star product. But we do not have a shuffle version of product, but instead, so left-hand side is a linear combination of formal indices of K shuffle L is equal to a single finite MZV, Zk concatenated L. So this L bar is a reversal of L. And this absolute value sign is a weight of L. And by numerical experiments, we conjecture that these are enough to deduce all linear relations of finite MZVs. Okay, so this gives you a fairly big class of relations among finite MZV. So now, so this is one of the most exciting part of our discovery, the finite real MZVs or symmetric MZVs, it's called. So we have a real counterpart of finite MZVs. So what that mean? So we have found an object in a real world which seems to satisfy exactly the same relations as this finite MZVs. So finite MZVs lives in a ring A, which is a direct product of finite fields modulo finite direct sum, right? So totally different world than the real numbers. So we give you a kind of a down-to-earth way of definition of these symmetric MCVs. So Ki are any positive integers, tuple of positive integers. S upper bullet, so bullet represent either a star or shuffle. And the right-hand side is a sum of products of regularized MZVs with this sign. So here the bullet is either star or sha, and zeta star or zeta sha are two regularized values. So so if k, so this ki up to k1 up to ki, and so when ki is 1, this is divergent, so we need to regularize. And we change the order of the remaining ki plus 1 to kr, so this is reversal. So if ki plus 1 is 1, there's a problem, so regularized value is needed. So we put the sign of the weight of this second one, okay? And from 0 to r. So when I equals 0, this is empty. So zeta something of empty is 1. That's a convention. So this definition is very strange looking, but star version has an interpretation as this is MZV-like sum, but this sum runs over all positive or negative integers, non-zero integers, with an order, it's a strange order. 1 is less than 2, less than up to positive infinity, and which is less than any negative integers. And minus 1 is the largest. Then we can arrange this into this definition. Anyway, there are two versions of this capital S bullet, S star and S sha. And we can show by using the the relation of two regularizations that these values are in general different, but it's the same modulo pi squared in the ring generated by classical MZVs. So modulo pi squared means the difference of left-hand side and right-hand side is pi squared or zeta 2 times some combination of MZVs. So this justify the following definition. So we define an element written as zeta sub s of k1 up to kr in a quotient ring z modulo pi squared z by one of these s guy modulo pi squared. Yeah, we recall again that kr may be 1, and this calligraphic z is the Q algebra generated by classical MZVs, the space spanned by all MZVs. Okay. So let's look at an example of depth 1 and depth 2. So first, the depth 1. So by definition, this capital S bullet of k is equals to minus k minus 1 to the k times zeta bullet of k plus zeta bullet of k. So whichever we use the bullet, this is when k is even, that means k is bigger than 1. So this is convergent, and this is twice of zeta k. And when k is odd, simply this cancels. This minus 1 to the k is minus 1. So this is simply 0. Right? But because of the result of Euler, so zeta k even is a multiple of pi squared. It's power of pi. So hence, by our definition, zeta s of k is equals to 0 by Euler. Yeah? The depth 2 case, this is a rather non-trivial computation, which we omit, but the result is zeta, S bullet of k1, comma k2 is congruent to 0 modulo pi squared when the weight k1 plus k2 is even, and when the weight k1 plus k2 is odd, this is congruent modulo pi to this single zeta, the multiple of single zeta. Hence, in this quotient ring, z modulo pi squared z, this is equal to, this is a typo. Sorry, this capital Z is not a capital Z, it's zeta. I'm sorry, this is a typo. Zeta, Riemann zeta of k1 plus k2 modulo pi squared. But remember, in the finite MZV case, the single zeta sub a of k was 0. And the depth 2 one is this one. Yeah. So this is the same, but this is a typo. So this zeta modulo pi squared. This is this. So very, very similar. Yeah. So now comes our main conjecture. So the Q algebra generated by this finite MZV is isomorphic to this quotient of real MZVs modulo pi squared under this correspondence. So the conjecture is that there is an isomorphism between two Q algebra, Z sub A, ring of finite MZVs, and this ring of real MZVs modulo pi squared, and under which this zeta sub A and zeta sub S exactly corresponds. So if we assume the direct sum conjecture, the weight, if the weight is the gives us a grading, this explains the dimension conjecture, because the weight k piece is, if the weight is grading, then weight k piece is simply dk modulo, so pi squared has zeta weight 2. So dk minus 2, which is dk minus 3, which is a conjecture dimension of weight k part of finite MZVs. And if we believe this conjecture, and if we believe under this conjecture, this capital Zk corresponds to Riemann zeta modulo pi squared, then the question, capital Zk is non-zero, is equivalent to the question of zeta k for k odd, is not the multiple of zeta 2 in this ring of MZV. So none of these questions are verified. It's still widely open. But it's very interesting, I think. This seemingly totally different questions may correspond to each other. Or one instance of this sum formula for zeta A in the S version has exactly same shape as Saito Wakabayashi's formula, replacing capital Zk by zeta k modulo pi squared, which is due to Murahara. Yeah, this is the FMZB case. And there are many other relations holding exactly the same form for zeta A and zeta S. And the final theorem, we have S version of this double shuffle relations as well. So this has a strong support of our conjecture. But still, this is a finite MZV case. But conjecture is far from being settled. Instead, we do not know the ring ZA is non-zero or not. So that is the current status of knowledge. Okay, thank you very much for your attention. I stop here.
Thank you very much for this very interesting and inspiring talk, with full of open problems actually, and which is current very nice results. Are there any questions or remarks? Actually, I have one bad question. I cannot say. Actually, for the dimension guess,
Yeah.
having results on Padovan numbers as a number theory it's a little bit surprising for me. Not Fibonacci or Lucas, somehow less famous sequences.
Yeah.
Did you surprise? I mean, are you surprised also with this sequence when you see the result?
Yeah, it was sort of surprising, but the deep theory behind that, like Grothendieck Teichmüller group or some sort of the algebra, this dimension conjecture has a kind of a strong support from that theoretical background, and this naturally arises in the certain structure of free Lie algebra having generated at each odd weight at 3, 5, 7 something. Yeah. So, but if you look at the so-called Euler sums, you allow the plus or minus signs on the numerator instead of one of definition of MZVs. It's called Euler sum. Then the dimension conjecture is a Fibonacci. Yeah.
Oh.
So lots of mysterious things
Yeah, very
going
interesting
on.
results.
Mm.
Thank you. Any questions? Thank you to the speaker again.
Thank you
And
very much.
from your colleagues and from your students, there is a small surprise for you. Please let me show you.
Oh. Oh,
Moment.
lots of.
Okay. A video. Link.
Oh. Oh, who wrote that? Oh, very nice. Thank you very much. Oh,
Please
yeah.
enjoy.
Now I notice several Japanese. Oh, how did they know that?
I am Shingo Saito from Kyushu
Oh.
University, Japan. I first met Professor Kaneko when I was a postdoc here at Kyushu University. Although I am not a number theorist by training, Professor Kaneko greatly expanded my horizons in number theory and profoundly influenced my understanding of what mathematics is all about. Also, as a colleague here, I would like to express my deep appreciation for Professor Kaneko's tremendous contribution to the administrative work at Kyushu University. Thank you very much, Professor Kaneko, for your kindness and support, and I wish you all the best.
Oh, thank you very much, Saito-san. Oh. Wow.
Hello, Kaneko-sensei. I'm very happy to be included in this message. 金子先生はいつも、私が困った時に助けてくださってありがとうございました。私が一度数学をやめて戻ってきた時にすごく一人ぼっちだったんですけれども、その時に私にこう手を差し伸べてくださったのは金子先生だけで、そのおかげで今私がこうして数学を続けていられていると思っています。
No.
ありがとうございました。先生は理解がされてもまたこう数学の世界を続けていらっしゃると思いますので、これからもぜひとも見守っていただければと思います。これからもよろしく。
Very gradually.
Congratulations.
ありがとうございます。Thank you. Thank you very much.
Hello, Masanobu.
Oh.
Many greetings from Durham. In more than 30 years since we first met in Kyoto, I cherish many wonderful memories from my stays in Fukuoka and from your visits to Europe, Germany, and UK. And right now we have a surprise visitor here in Durham.
I'm a surprise visitor. I'm spending 3 weeks with Herbert, giving a series of lectures, just as I did in Kyushu 35 years ago, but this time without you to take your wonderful notes in Japanese. And talking about you and thinking about you and thinking of all of the years and the many, many visits, in my case, in even more countries with you in Italy and France and Germany, and hoping that we'll see you again many times in the coming years and maybe even write one more paper together.
Well, thank you very much. Wow. It's amazing. Oh, fantastic. Thank you.
You're welcome. And I have one last minute message from Professor Kyushu. Just a moment, please. I will also show it to you.
Josaku-kun.
Just a moment, please. Actually, with my students, thank you very much to Murat, Utku, and Salih. We tried to reach all your collaborators and students from your papers. So in April, I sent an email to the group, and some of the mails were just a moment. Some of mails were not working, but I get some videos. And lastly, from Durhan, from Don Zagier. Actually, he is here in my office.
Yeah, I noticed.
Like he's every rest in peace. And Zagier and Fry, These are there in my office. So it was also for me, it was nice. And last message is now I will show you. It's a last minute message.
Ah, 皆さん、こんにちは。私はジョハクです。中国から来ました。2019年から2020年まで、私は九州大学でカーネギー先生に留学していました。もう7年経ちました。本当に早いですね。先生には本当にお世話になりました。ありがとうございます。
You're welcome.
拓殖語もますます素敵な毎日を過ごくしてください。
ありがとう。Thank you
あ
very
りがとうござい
much.
ます。
谢谢，谢谢。
So I will also share the video with you. And I know you from your good papers and very good contributions to the mathematics world. But last year, when I was giving a talk in Kyushu, I met you in person. And normally, till to all my talks or lectures, I was not excited. And actually, I told to my students about this last year, this Fukuoka event, that when I saw you in the lecture room, I was really very, very excited to see you over there. So it was really inspiring for me. So I think in Japanese culture, when you have some retirement, just I learned it from AI actually. For the second part of your life, I wish you success, happiness, and good health with the second part of your life. So thank you very much for this very nice talk, very inspiring talk. For all participants, thank you very much for your interest to Bilegic Algebra and Number Theory Seminar. This was the last talk of this semester. We will resume with new talks, hopefully in September or October. Keep in touch. Okay, thank you.
Thank you very much.
ありがとうござい
Great
ます。
surprise. ありがとうございました。Thank you.
Bye
See you.
bye.
Yeah, bye. Thank you very much.